with Neptune raising concerns among examiners and space enthusiasts. Notable scientists, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the potential consequences of a collision between Pluto and Neptune. But how did Pluto end up on a possible crash course with its distant neighbor, and what might this cosmic event mean for us here on Earth? Pluto, once classified as the 9th planet in our solar system, was demoted to dwarf planet status due to its peculiar orbit. Despite this change, Pluto continues to captivate astronomers and the public alike. Experts have focused on the region where Pluto's orbit intersects with Neptune's, warning of the possibility of a collision between the two celestial bodies, which could pose a significant risk to Earth. Pluto's orbit around the Sun is distinctive primarily because it deviates significantly from the almost circular orbits of the other planets. Its elliptical orbit stretches far from the Sun, and it remains incomplete even after decades of observation, having only partially completed a full orbit since its discovery in 1930. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's. For 20 years of each orbit, Pluto ventures closer to the Sun than Neptune, which defies expectations. However, despite this seeming danger, no collision has occurred. This is due to the gravitational influences of other planets and the unique dynamics of the Pluto-Neptune system. Pluto's orbit is tilted at a 17 degrees angle to the ecliptic plane, and its path is further complicated by its oblong shape. Yet the gravitational interactions between Pluto-Neptune and other giant planets in the solar system prevent any catastrophic events. The three-body problem in space mechanics explains the complex interactions and gravitational forces between Pluto-Neptune and the Sun, making precise predictions about their future trajectories challenging. Astrophysicists believe that Pluto and Neptune's resonance, their orbits being linked in such a way that Neptune completes 3 orbits for every 2 of Pluto, helps prevent a collision. Additionally, other massive planets like Jupiter and Saturn play roles in stabilizing Pluto's orbit, contributing to the long-term stability of the system. These gravitational interactions ensure Pluto's path around the Sun remains stable over billions of years despite its seemingly chaotic orbit. This intricate system of forces is crucial to the broader understanding of planetary motion and celestial mechanics. Even though Pluto's orbit appears erratic, the cumulative effects of these gravitational forces keep the dwarf planet in check. This stability is essential for maintaining the balance and order of our solar system. The study of such phenomena helps astronomers understand the intricate dynamics of planetary systems and the potential risks they pose not only to other celestial bodies but to Earth as well. Neil deGrasse Tyson, a prominent astrophysicist, has expressed concern about the potential for a collision between Pluto and Neptune, which he sees as an opportunity to further our understanding of celestial mechanics. Tyson's viewpoint is grounded in the evolving nature of our knowledge of space. He views the renaming of Pluto from planet to dwarf planet not as a demotion but as an acknowledgement of the complexities of celestial bodies and the growing depth of our understanding of the universe. Tyson, along with others, warns that even the seemingly stable orbits of distant planets are subject to change due to these complex interactions. If a collision were to occur, it would have significant consequences, potentially releasing immense amounts of energy and altering the orbits of other bodies in the solar system. For Neptune, such an event could impact its atmosphere and orbital path, while Pluto, being much smaller, could be severely damaged with debris scattering across the solar system. Michio Kaku, a theoretical physicist known for his work in string theory, offers a different perspective. He sees the study of Pluto's orbit and its interactions with Neptune as a window into the broader future of space exploration. Kaku believes that understanding the gravitational interactions of planets can provide valuable insights for future space missions, especially when it comes to exploring the outer regions of our solar system. Moreover, the study of Pluto's orbit could even inform our understanding of string theory, offering clues about fundamental forces and the nature of the universe. Both Tyson and Kaku emphasize that even though the chances of a collision between Pluto and Neptune are low, the study of these complex systems is vital for our understanding of the universe. It allows scientists to explore the fundamental principles of space, from gravity to the dynamics of celestial bodies. The potential collision, while remote, could serve as a reminder of the unpredictability and vastness of the cosmos. In addition to the potential for Pluto and Neptune to collide, there are other more speculative events that could lead to planetary catastrophes. Rogue planets, for instance, which are ejected from their original solar systems, may wander through space and potentially impact other planetary systems. However, the likelihood of such an event is incredibly low due to the vastness of space. Even so, understanding these dynamics is crucial for the advancement of astronomical research and the development of future space missions. Pluto and Neptune. A cosmic dance. One of the most intriguing aspects of the relationship between Pluto and Neptune is how their orbits while crossing never result in a direct collision. This paradox is due to a delicate gravitational dance between the two bodies which has been understood through complex mathematical models and simulations. Pluto's orbit, as mentioned earlier, is not only elliptical but also highly inclined and eccentric compared to the circular orbits of the other planets. Its orbit takes it from as close as 29 astronomical units, AU, to as far as 49 Australian dollars. When Pluto's orbit intersects Neptune's, the two bodies appear as if they could collide, but due to gravitational resonance this is avoided. Pluto and Neptune are in what is called a 3.2 orbital resonance, meaning that for every 3 orbits that Pluto completes around the Sun, Neptune completes 2. This resonant relationship ensures that while their orbits cross, the positions of Pluto and Neptune never align in such a way that a collision occurs. This resonance caused by their gravitational interaction effectively locks Pluto's orbit in a stable pattern, preventing it from getting too close to Neptune. The reclassification of Pluto. Pluto's reclassification from planet to dwarf planet in 2006 remains one of the most significant events in the field of astronomy. For over 75 years after its discovery, Pluto was considered the 9th planet in our solar system. It was discovered in 1930 by Clyde Tombaugh at the Lowell Observatory in Arizona and was viewed as a distant, mysterious object located far beyond Neptune. However, astronomers began to realize that Pluto was not alone in its size and characteristics. In the late 20th century, the discovery of the Kuiper Belt, a vast region beyond Neptune filled with icy bodies, opened up a new frontier in planetary science. It became clear that Pluto was just one of many similar objects in this distant region, leading to the question of whether it should be considered a planet at all. In 2006, the International Astronomical Union, IAU, officially redefined the term planet and excluded Pluto from this category. According to the new definition, for an object to be considered a planet, it must meet 3 criteria. It must orbit the Sun. It must have cleared its orbit of other debris. Pluto failed the 3rd criterion because its orbit overlaps with that of other Kuiper Belt objects. The 3-body problem: chaos and stability in space. The 3-body problem, which describes the gravitational interactions between 3 celestial bodies, is one of the most complex and fascinating challenges in classical mechanics. In the case of Pluto, Neptune, and the Sun, the 3-body problem plays a critical role in determining the orbits and interactions of these bodies. While the basic laws of gravity are well understood, predicting the precise motion of 3 interacting bodies is far more difficult. Understanding these interactions is crucial not only for studying our solar system, but for predicting the future of planetary motion throughout the galaxy. The 3-body problem is a well-known issue in celestial mechanics, describing how 3 massive bodies such as Pluto, Neptune, and the Sun interact through gravity. Unlike 2-body systems, where an orbit can be predicted with relative simplicity using Newton's laws, 3-body interactions create complex and often unpredictable motions. In the case of Pluto and Neptune, their gravitational relationship is further complicated by the presence of other massive planets like Jupiter and Saturn. These additional gravitational influences create minor perturbations in Pluto's orbit, yet the system remains remarkably stable over long timescales due to the 3.2 orbital resonance between Pluto and Neptune. This resonance prevents Pluto from approaching Neptune too closely, acting as a protective mechanism that has kept their orbits from colliding for billions of years. The study of such resonances has broader implications, as similar patterns have been observed in exoplanetary systems beyond our solar system. By understanding how gravitational interactions stabilize or destabilize planetary orbits, scientists can refine models predicting the long-term behavior of planetary systems. Could Pluto's orbit change in the distant future? While Pluto's current orbit is stable, astronomical timescales are vast. Over millions or even billions of years, gravitational influences from other celestial bodies, including rogue asteroids, passing stars, or even an undiscovered massive object in the outer solar system, could subtly alter Pluto's orbit. One speculative theory involves the hypothetical Planet 9, a proposed but still unconfirmed massive planet lurking beyond the Kuiper Belt. If such a planet exists, its gravitational pull could gradually shift the orbits of distant objects, potentially affecting Pluto's trajectory. While this remains purely hypothetical, the idea highlights how even small changes in gravitational forces can have significant long-term consequences in planetary motion. Additionally, the Yarkovsky effect, a force caused by uneven heating and cooling of celestial bodies, could also play a role in altering Pluto's orbit over millions of years. This effect is more pronounced on smaller asteroids, but theoretically could influence Pluto's long-term path. The broader impact of Pluto-Neptune studies. The study of Pluto's orbit and its relationship with Neptune extends beyond just these two celestial bodies. It helps astronomers develop a better understanding of exoplanetary systems. Many of the planets discovered in distant star systems exhibit orbital resonances similar to those seen in Pluto and Neptune. Understanding these interactions in our own solar system provides insight into how exoplanets behave and evolve. The early solar system. Studying Pluto's interactions with Neptune helps scientists reconstruct the history of our solar system. It provides clues about how the outer planets migrated over time and how the Kuiper Belt formed. Future space missions. Any future mission to explore Pluto or the Kuiper Belt must account for these gravitational interactions when plotting spacecraft trajectories. Understanding Pluto's orbit ensures that future probes can navigate safely and efficiently. Although current models suggest a Pluto-Neptune collision is highly unlikely, a hypothetical impact between the two bodies would be a cataclysmic event. Given Pluto's icy composition, a collision with Neptune would likely shatter Pluto into countless fragments, some of which could be ejected into interstellar space. The remaining debris could either be captured into new orbits around Neptune or spread throughout the solar system. The impact would also alter Neptune's atmosphere and potentially affect its moons. While the event wouldn't directly threaten Earth, the redistribution of debris could lead to an increased presence of space dust or small Kuiper Belt objects drifting inward. Such an event would provide an unprecedented opportunity for astronomers to study planetary collisions in real time.